Okay, now what I want to talk about before I start the lecture is the take-home assignment. Here, this is the take-home assignment. I talked about it yesterday. You should be able to find it in the summative assessment folder. If you couldn't find it yesterday, then that problem has been solved. You will be able to find it there today. You'll find two things. You'll find this document, which contains the exercise, and you'll find the data set, which is a Stata data set, which you need to read into Stata. Now, what I warned you about yesterday is it's quite a long exercise and it's in many parts. Don't worry if you can't do the later parts, because in 2 weeks' time, you'll be able to do the whole thing. My advice to you is start it as soon as possible. Start working on it. Read the data, start working on it. Just get as far as you can. You will be able to get to part C, probably B, at least part B. So can I just make sure that we all know what to do? I'm going to stop sharing this and I'm going to share Stata. Okay, now what you have to do is you have to copy the data set. The data set is called house_2021. You need to copy that file from Blackboard to your own file space, somewhere in your own file space, the place where you normally store data files or data sets. Maybe you create a folder. Maybe you should create a folder called Take Home Assignment or something. Then what do you have to do? You go File, Open, and then you find the folder where your data set is, and then you select it, Open. Right, and then the command that we've just the command that we've effectively used to read the data set is this command here, use, and then we've got a long path name finishing with the name of the data set. And up here, we have a list of all the variables that are in the data set, starting with property number, price in thousands of pounds, number of bedrooms, and so on. If you want to look at the data, you click on Data Editor. Data Editor Browse, and then you see that you have the column. The first column is the house number, and house number goes from 1 to 3175, because there are 3,175 properties in the data set. This variable here is the price at which the property was traded. So the first house was sold for £346,670. Remember, the price is in thousands of pounds. This number is in thousands. This first property has 5 bedrooms, 1 bathroom, 3 recreation rooms, no garages. It's type 7. Type 7, I think, is maybe semi-detached. It's in postcode 4, that's NR4. It has 150 square meters of floor space. It has no double glazing, no central heating. It has a garden size of 290 square meters. It has a pollution level of 35, a noise level of 35. It's 96 years old. Now that's the age of the property. See, it's not the age of the person who lives in it, it's the age of the property. So some properties are very old, and we're interested to know whether that has an effect on price. And then we've got the month. Now, month is 1 in January 2015, 2 in February 2015, and so on. Right at the end of the data set, we have some properties that were traded in October 2021, which is the month that we are currently in. Okay, so that's what the data set looks like. Just to start you off, I mean, the first question says compare the mean and the median of price and obtain a histogram of price. Well, price, well, you don't have to type variable names. The best thing to do is to select variables from the variables window. So I go hist price, and there is the histogram of price. Now, if you're asked to describe the distribution, the thing to do is to definitely say what the lowest and highest number is. What's the lowest and highest price? Give that information, and then give information about the overall shape. Is it a unimodal distribution? That is there just one peak or is there more than one peak? Is it a skewed distribution? Is this tail, or is this tail of the distribution longer than this tail? If this tail is longer, then you say it's a distribution that's skewed to the right or positively skewed. If you go summarize price, then you get some information about descriptive statistics of the variable price. You get the mean, the minimum, the maximum, which is part of what you need. Something else you need is the median. Well, if you go summarize price detail, and these commands are given to you in the question paper. I'm telling you what commands to use in these early parts. If you use summarize price detail, you not only get the mean and the well, you get the mean, which you need. You also get the median. The 50% number here is the median price. That is the price that you get if you order all the observations from lowest price to highest price. The one in the middle of the list is the median price. Now, what does it mean? What does it tell us? That if the mean is 273, which is higher than the median, what does it tell us about a distribution? Think about that. If the mean is higher than the median, what does that tell us about the distribution? And then in part B of the question, we have to use this command, table P code. Well, if you go table P code, then what you get is you get the information about the number of properties in each postcode. So we see fairly even distribution between the 8 postcodes. NR2 is the most common. NR8 seems to be the least common. But what we want here is not the frequency. We want the mean price. And to get this, we go stat mean price, which is an option. Okay, remember, statter commands consist of 2 parts: the main part of the command, and then a comma, and then the option. The option in this case is stat, and in the brackets we specify that we want the mean of price. So what we've got here is we've got the mean price in each of the 8 postcodes, and we see that the postcode with the highest prices is NR4, 380,000. The postcode with the lowest prices seems to be NR3, average 224,000. So that's how you answer part B of the question. And then the most important thing we're doing in this exercise is obviously regressions. So the part C is the first regression. So to do the regression, we go regress. The dependent variable is price, and we want to know what determines the price of a property. Well, obviously, all of these things determine the price, but the question C asks us to do the following. Estimate a regression model with price as the dependent variable, and square meters, that's the floor space, beds, number of bedrooms, number of bathrooms, number of recreation rooms, garages as quantitative explanatory variables, and a set of dummy variables for type. Well, I haven't explained this to you yet in lectures, but I'll just show you it now. If we go I.type, then we get what we need, which is a set of dummy variables for house type. Type is a variable which is 1 if the property is an empty plot of land, 2 if a flat, 3 if a bungalow, 4 if a chalet, and so on. It's the type of property. So let's see what happens when we run that. We get the usual things. We get a table of results with the usual things at the top. We've got the sample size, the R squared, the analysis of variance table, and we've got a large table of estimates. And this is because it's a multiple regression, okay? The regressions we've done so far, we only have 2 rows here. We have a row for the intercept and a row for the explanatory variable. Well, here we've got a number of explanatory variables: square meters, beds, baths, recreation rooms, garages. Number of square meters definitely has a positive effect on the price. We can see that. I mean, most things are significant here. We can see that from the p-values. One of the questions you see later on is why does the number of bedrooms and the number of recreation rooms have a negative effect on the price? Or at least, why do those variables appear to have a negative effect? That's something you have to think about. I will come back to that in a later lecture. But just for now, what's going on here? We have what are called 7 dummy variables for type. This is a dummy variable for type 2, type 3, type 4. Now, when you have a group of dummy variables, one of them is excluded. So type 1 is excluded, and that's called the base case. What we see here is that, let's look at the last one, type 8. Type 8 is detached houses. Detached house. What we see here is that a detached house is worth £63,000 more than a type 1. A type 1 is an empty plot of land. So when you're interpreting these numbers, you have to compare them with the base case, which is the missing type, which is type 1. Okay, well that might not be clear because I haven't actually given you a lecture on dummy variables yet. That will be the first, I think, the first lecture of next week. So what you see here will be clear after the lectures next week. Anyway, that's the answer to part C, and hopefully that'll give you an idea of how to start this exercise. Any questions? All makes sense. Okay, good. Thanks. Let's see. What is the meaning of base case? I'll explain that when I give the lecture on dummy variables. As I said, sorry, I just need to share the lecture notes. Bear with me a second. Okay, what is meant by base case? Well, the lecture today is on the classical assumptions. I think the next lecture, let's see. Oh no, the next lecture, the first lecture next week is on testing in the multiple regression model. And the lecture on Tuesday of next week, so this time next week, I will give this lecture, which is on dummy variables, and that starts on page 44 of the lecture notes. So dummy variables will be much clearer after I've given that lecture. Before that, we've got this lecture on the classical assumptions, and then a lecture on Monday of next week on testing in the multiple regression model. Okay. So we're on page 34 of the lecture notes. The classical assumptions. I've already told you that ordinary least squares is a desirable estimator because it has desirable theoretical properties, for example, unbiasedness. Remember what that means. That just means that if you do ordinary least squares regression every day, then sometimes the slope estimate is too high and sometimes it's too low, but on average, it's correct. It equals the thing that you're trying to estimate. It equals the parameter. That's what unbiasedness means. There are other desirable theoretical properties. In the context of multiple regression, we're now in a position to consider these optimal properties more formally. This is the Gauss-Markov theorem. Consider the multiple regression model. So we're being general here. We're no longer restricting attention to the simple regression model. We've got a situation with k parameters. So it's a fully general model. N observations, k parameters. That means there are k minus 1 explanatory variables because the first parameter is the intercept and it doesn't have an explanatory variable. This is the Gauss-Markov theorem. Of all linear unbiased estimators, the ordinary least squares estimator has the smallest variance. That is, the ordinary least squares estimates the parameters more precisely than any other linear unbiased estimator, given that certain assumptions are met. Now, I've emphasized that because it's important. Ordinary least squares is the best estimator, but only if a list of assumptions is met. So when you use ordinary least squares, you have to check that these assumptions are all met. And that's what I'm talking about today. If these assumptions are met, the ordinary least squares estimate is said to be the best linear unbiased estimator, blue, B-L-U-E. This is the Gauss-Markov theorem. It's the most important theorem in econometrics, central to econometrics. The fact that we can use ordinary least squares and it gives us the best estimates, but only if these assumptions are met. The assumptions are important. If they do not hold, ordinary least squares is not a best linear unbiased estimate. They are known as the classical assumptions, and there are 6 of them. So I'm going to go through each one. I'm not going to talk in detail about them. I'm just going to tell you what they are and give an example. Later on, we will consider some of them in more detail. So like, for example, some of these assumptions, I'm going to devote a whole lecture to talking about them later in the module. Assumption number 1 is correct specification. This assumption says that the model specified in 1, the model that we write down here, whatever y is and whatever the x's are, is the true model. Okay, so we are assuming that the model that we write down and that we estimate using the regress command in Stata is the true model which is generating the data. This is a difficult assumption to satisfy. Common violations are: 1, wrong functional form. For example, estimating a Phillips curve using a linear specification rather than a reciprocal specification, and we'll see an example of this in workshop 4, question 3. By the way, this is workshop 4. Now, workshop 4 requires you to use some data sets, Milk and Phillips. The data sets aren't there yet, but I promise I'll put them on Blackboard later today. So if you want to try out this workshop exercise in advance of Friday, you can do. So anyway, wrong functional form. For example, estimating a Phillips curve using a linear specification. Well, let's just say, as we will see on Friday, you have data on inflation and unemployment. So the x variable is unemployment and the y variable is inflation. Well, the data that you obtain, the data that you see when you read this data set, has this nonlinear form. It's not a straight line. Okay, it's what we call a Phillips curve. It's old data. It's data from before 1970, but it doesn't matter. It's still interesting. So if you try to fit a straight line through this data, it's obvious you're doing something wrong. You're trying to fit a straight line through something which is not a straight line. So that's an example of wrong functional form. Remember, the appropriate model when you have a Phillips curve is not y equals beta 1 plus beta 2x. That's wrong. Instead, use a reciprocal model. Y equals beta 1 plus beta 2, 1 over x. So this is the correct functional form. Well, it may still be incorrect, but it's more, if the data looks like this, This model is more likely to be the correct model than this one. So all I'm doing here is I'm giving you an example of a situation in which the wrong functional form is used, and this is an example of a violation of assumption 1. A second possible violation of assumption 1 is omitting a relevant variable. For example, this is another example we'll see in workshops, omitting interest rate from an aggregate consumption function. If you're a macroeconomist and you want to estimate the marginal propensity to consume, you do a regression of aggregate consumption on aggregate income. However, aggregate income is not the only variable that affects consumption. There are other variables, including the interest rate. And if you omit the interest rate, then you have a misspecified model and you're violating the assumption of correct specification. So basically, if you leave out a variable that should be there, that's a violation of assumption 1. Number 3, inclusion of an irrelevant variable. Now, what is an irrelevant variable? This is a variable that is not important. A variable that does not affect the variable that does not affect the dependent variable. If you include an irrelevant variable, then it's a violation of assumption 1. It doesn't cause a bias in your estimates, but it causes an imprecision. If you include things that shouldn't be there, if you include things that don't need to be there, then you are losing precision in estimation, and that's why you no longer have a best linear unbiased estimator. Now, if you're asked for an irrelevant variable, like you've got to be careful, because it's quite hard to think of a variable that's completely irrelevant. Because if someone says, think of a variable that's irrelevant in explaining economic growth, you might say something like football results. Football results are irrelevant in explaining economic growth. Well, you'd be wrong that football results are irrelevant, because people have published papers proving that, for example, a country winning the World Cup has a burst of economic growth in the following years. So, as I say, when you really have to find a variable that's truly irrelevant, it can be quite hard. This is a variable that's irrelevant. Household's telephone number. If you have access to a household's telephone number in your data set and you include that as a quantitative variable in the regression, then I think it's safe to assume that is an irrelevant variable and it shouldn't be there. That's just an example of an irrelevant variable. Okay, that's assumption 1, the assumption of correct specification. Assumption 2 is the assumption that the error term equals 0 for all I. Now remember what the error term is. The error term is this thing we add on at the end. The thing that we add on at the end, which makes the theoretical model applicable to real data, because we need an error term, because households' behavior or the behavior of individuals or firms or the behavior of the economy has a random element. We can never predict it exactly. That's why we need the error term. But the error term has important properties, starting with the expectation of the error term equals 0. What that essentially means is if we have a regression line, and that's the true regression line, then essentially, and I've told you this before, we're saying that if we consider a particular value of x and we ask what's the distribution around the true regression line, then the distribution of data, the distribution of points above and below the true regression line is on the true regression line on average. On average, we're on the true regression line. We're sometimes above, sometimes below, but on average, we're on it. That's what we mean when we say the expectation of the error term equals 0 for all I. This assumption says the expectation of the error equals 0 for all observations. That is, if we consider the distribution of points around the true regression line for a given x value, that's the diagram I've drawn here. This distribution has population mean on the true regression line. A violation of this assumption occurs if we're attempting to estimate a production function. Now, this is a very precise example. We want an example of a violation of this assumption. The best example is this. Let yi be output of firm I, and li be the number of workers hired by firm I, and ki is the number of machines, capital. See, labor, capital. Then we might estimate this model. Output of the firm depends on labor and capital, and there's an error term. Okay, the error term, someone's asked a question. The error term is the random variable that you put in your model. It's a random variable, so it's slightly abstract because we can't think of it taking particular values. But then when we estimate the model, we obtain a fitted equation, and the residuals, which are the difference between the actual data and the fitted values, the difference between the actual y and the fitted y are what we call the residuals, and the residuals we call ui hat. So the question is the error term and the residual the same thing? Well, they're very similar. It's just the UI, think of the UI as the theoretical version of it. So the thing that appears in the theoretical model. The UI hat is the residual, and that is the values that's actually taken by the error term. Okay, but back to this example. If we're estimating a production function, well, what is unique about model 2 is that the deterministic part of it, which is y equals beta 1 plus beta 2 L plus beta 3 K without the error term, is a production frontier. And actual production can never exceed it. Now, what I mean by this is, let's draw a graph. Let's draw a production frontier. Y is output. And X is, well, we're not calling it X, are we? We're calling L. L is labor input, number of workers. Now we want capital as well, but we've only got 2 dimensions to draw the graph. So let's just assume that output depends on labor. And output, obviously, if you don't have any workers, you can't produce anything. So maybe, well, so we start at the origin and we've got a line like that. Now the point about this line is that it's a production frontier, which means that firms can be close to it. If they're very efficient, they can be very close to this line, but they can't be above it because it's a limit to production. So some very productive firm might be on the production frontier, but no firm is above the production frontier. So every firm is below the production frontier. So the error term is always negative. The error term is always negative, it's never positive. So that's the point that's made here. All the observations are below the regression line that is being estimated. The error term UI in 2 represents the productive inefficiency of firm I. So the further a firm is below the line, that is a measure of their inefficiency. This firm here is very inefficient because they're a long way below the line. It's always a one sign negative. It follows that the expected value of the error term must be negative. What we're saying here is if all the error terms are negative, then the expected error term, remember expectation, capital E just means the expectation of a random variable, and that's like the mean. Well, if all of the errors are negative, then the mean of the error is negative. Hence, we have a violation of this assumption. Hence the violation of assumption 2. Now, what's the consequence of this? If this is your data and you use ordinary least squares, think what's going to happen. You're going to fit a straight line through this data set using least squares, and the least squares line will not be the thing that you're interested in. It'll be something below the thing you're interested in. So the OLS line, because it passes through the middle of the data, will give you the wrong line. What we want is the frontier. So we want something that tells us where the top of the data is. Ordinary least squares does not give us that. So it's obvious, it's easy to see why ordinary least squares is not a good estimator when you're estimating a production frontier. So that's a nice violation, nice example of a violation of assumption 2. Assumption 3, there is no perfect linear relationship between the k explanatory variables. Go back to the model. Notice we've got k explanatory variables, or strictly speaking, we've only got k minus 1, x2, x3, up to xk. Now, the assumption we are talking about here is that these variables, these x variables, are not perfectly related with each other. This is the assumption. It's best understood in the context of a single example. Consider this cross-section model. Household expenditure. We were looking at an example like this in the first week. We had household expenditure, we had data on the number of adults, the number of children. Well, if you do a regression with household expenditure as the dependent variable, and you want to explain household expenditure in terms of the number of adults and the number of children and the number of people, well, if you do this, then there's a problem, because the number of people equals the number of adults plus the number of children. So there is a perfect linear relationship between the explanatory variables of the model. The model is said to suffer from perfect multicollinearity. This makes it impossible to disentangle the separate influences of the three variables, and therefore impossible to estimate the parameters. So if you try to do this in stata, if you do regress expenditure, adults, children, people, then it won't work. Now, stata understands this problem. Stata will tell you that you have a perfect linear relationship between your three explanatory variables, and it will remove one of them for you, and it will give you estimates of maybe it'll remove one of them. But that's the solution. All you have to do is to leave out one of the three variables. When you have perfect multicollinearity, there is always a simple solution. Leave out one of the variables, remove it from the model, and that solves the problem. So in a sense, this is the easiest problem of the 6 assumptions. This is the easiest violation to solve. That's page 35. Page 36. Ah, yes. Now I'm mentioning here near multicollinearity, which is a different problem. Notice the violation. When this assumption is violated, it's a problem of perfect multicollinearity. When the assumption is violated, it's because you have perfect multicollinearity. A different sort of problem, but closely related, is near multicollinearity. This is often a problem in time series models. This occurs when explanatory variables are highly but not perfectly correlated with each other. And when I talk about correlated, when I say correlated, I just mean similar. I just mean if two variables are highly correlated, that just means they go up and down at the same time. They look similar to each other. They behave in similar ways. Now, if two variables are similar but not the same, this makes it hard but not impossible to disentangle the variables' separate influences, and it results in high standard errors and lack of precision. However, near multicollinearity does not amount to a violation of assumption 3. So for assumption 3 to be violated, you have to have this situation of a perfect relationship between the variables. Assumption 4. Assumption 4, excuse me for 1 second. Assumption 4. This is this. Assumption 4 is that the variance of the error term is sigma squared for all I. Now we're talking about the error term again. We've already said the expectation of the error term is 0. That was assumption 2. Now we're saying the variance of the error term, which, remember, variance is just a measure of the spread of the error term. We're talking about this error term. The variance of the error term is sigma squared for all observations. That is assumption 4. Now, the crucial thing about this assumption is there's no I here. So what we're saying is that the variance of the error term is always the same. And this is the assumption of homoscedasticity. Variance of the error term equals sigma squared for all observations. This is the assumption of homoscedasticity. And that's because the word skedasticity it has the meaning of spread. We're saying that the spread is the same for all observations. This assumption is often violated in cross-section models. For example, let's consider this model. Y on X, a simple regression model where Y is expenditure on cars by household I, and Xi is income of household I. So what's this going to look like? Well, we're going back to talking about Engel curves here. We're considering what's the Engel curve for cars. Now, what does it look like? This is income, and this is Y is expenditure on cars. Well, I think it's safe to assume that cars are a luxury. Now, remember, when you have a luxury, low-income households consume 0. So low-income households spend 0 on cars. When income goes above a certain threshold, expenditure on cars becomes positive. And the higher income is, the higher the spending on cars that you might see. But the important thing about this is that some high-income households, let's make this more obvious. There's a household up here who buys a Rolls Royce, and there's a household down here who, although they're very wealthy, they earn a lot of money, they have a high income, they choose to spend a small amount on cars, because they choose to spend 0 on cars, because they prefer spending their money on other things. So this just reflects the fact that people are able to choose. And the key thing is that high-income households have a greater choice. So for high X, now actually X, the letter X is income, and these things I'm putting here are crosses, which represent points in the scatter. Don't get confused between these and this. X is the variable. But the point about this graph is that for high-income households have a greater choice about what to do with their money because there's more money there. Low-income households have much less choice, and that's the point that's explained here. Households with higher incomes have greater choice over how much to spend on cars. Some wealthy households choose to own expensive cars, and that's a household up there. Others choose to have no car, that's the household there. Poor households are restricted by a budget constraint to spend a small amount on cars, whatever their preference is. So there's a sense here that the scope for choice depends on the income level, and that's what gives us the violation of this assumption. Because if you look at this assumption carefully, this assumption says that the variance here, the spread, the dispersion, the length of the arrow that we're drawing here should be the same as the length of the arrow we're drawing here. But because of this thing about choice, the dispersion here is going to be much higher than the dispersion here, and that's a clear violation of assumption 4. Another way of saying this is that the variance of the error term, ui in 4, is higher for higher values of x. So yeah, I mean, we've got a regression line underlying this thing. The error term is the vertical distance of points from the line. Well, obviously, for high values of x, the error terms tend to have higher magnitude than for low values of x. So we can see that this cars to income example is a good example of a violation of homoscedasticity. And when we have a violation of homoscedasticity, it is referred to as the problem of heteroscedasticity. Now, the problem of heteroscedasticity heteroscedasticity, sorry, does not cause a bias in the estimates. However, the reason why it's considered to be a problem is that more precision could be achieved by attaching more weight to the observations for which the variance is low. Now watch the intuition here. When the variance is low, like here, low x, the points, we know for a fact that that point is close to the true regression line. Remember, we don't know where the true regression line is. We're trying to find the true regression line, but we know that that observation is close to the true regression line because the variance is lower here. This observation here, we don't know if how close it is to the true regression line. It might be close to the true regression line. After all, that observation is close to the true regression line. So we don't know whether this observation is close or far away from the true regression line because we don't know where the true regression line is. So in a sense, these observations down here are more valuable. They give us more information than these observations up here. So if we wanted to exploit this difference in information, we would attach greater weight to the observations down here than to the ones up here. Ordinary least squares does not do that. Ordinary least squares weights all of the observations equally, so it's not the best estimator. We could do better by weighting the observations according to where they are in the income distribution. Now, that's one problem, but that's not actually a serious problem, because if you have a large sample, then you don't really worry about precision and variance. For example, when you look at the house price data set, you've got over 2,000 observations. You might find that you have heteroscedasticity in that data, but this is not the problem. You know, low precision is not a problem because all the estimates are very precisely estimated. The standard errors are always low. So a more serious consequence of heteroscedasticity is this: the estimated standard errors are incorrect. This is because the formulae, for example, this formula here that we used to work out the standard error, this is the formula that we've been using to work out the standard error of the slope in simple regression. Well, this formula is derived, if you look up the derivation of this formula, there's no need to, but I'll just tell you, this formula is derived on the basis of homoscedasticity. If homoscedasticity is violated, that is, if the variance differs between observations, this is no longer the correct formula for the standard error. This means that if you have heteroscedasticity, so if your data looks like this, then yes, you can estimate the slope and get an unbiased estimate of the slope, but the standard error that you get using the standard formula for the standard error will be wrong. And of course, if your standard error is wrong, that means your t-ratio is wrong and your confidence interval is going to be wrong as well, because the t-ratio and the confidence interval involve the standard error. So that's a serious problem. The conclusions you end up with will be incorrect if you have the problem of heteroscedasticity. Okay, let's carry on. Assumption 5 is the assumption of no serial correlation. Now, what we're saying here is that the covariance between two errors in different observations is 0. So essentially what we're saying here is there's no relationship between the error term for observation I and the error term for observation J. It's not clear, may not be clear that that's I and J. We're talking about two different observations there, UI and UJ, I not equal to J. We're saying the covariance between the two error terms is 0. Well, I mentioned that right at the beginning. I said when you write down the food model, what we're essentially saying here is if one of the households, the first household in your sample overconsumes, so their error is very high, then that doesn't tell us anything about the second household. This is the assumption of no serial correlation or no autocorrelation. The assumption is often violated in time series macroeconomic models. due to the cyclical nature of macroeconomic variables. For example, consider the consumption function, CT. Now we're talking about a macroeconomic model here. CT is aggregate consumption. It's not household consumption, it's consumption in the economy in period T. So we're going to have time series data in order to do this. N time series observations, so annual data or quarterly data on consumption and personal disposable income. And you do a regression of C on Y. What are the parameters, beta 1 and beta 2, called? Well, beta 1 is what we call the level of autonomous spending. And it's like the intercept of a consumption function. You've got, this is a macroeconomic model. Don't think of a household, think of the whole economy. Aggregate consumption, aggregate income. The intercept here, beta 1, is what we call autonomous spending. Beta 2 is the slope. Now, beta 2 is the slope of the consumption function. So here we're asking if personal disposable income rises by $1 billion, by how many $1 billion does aggregate consumption rise? And what is the name of this quantity? Anyone know? What do we call this parameter in macroeconomics? It's called the marginal propensity to consume, or MPC, and it's a very, very important parameter in macroeconomic models. Anyway, this is the model that we're talking about. We're thinking about a simple regression of aggregate consumption on aggregate income, and we have data on these two variables, and we're trying to estimate the consumption function. As I've just said, there's the intercept and there's the slope. We've got consumption and we've got income. But the thing is, because this is time series data, this is a time series model, over time, because of economic growth, these two variables tend to rise over time. So over time, we're climbing up. Think of it like this. Over time, we climb up the consumption function. So 40 years ago, we were down here, and then the next year we were there, and the next year we were there, and we're gradually climbing up. But the point that we need to make here is that the way we climb up the consumption function over time is with a particular pattern. That is, we have a sequence of observations above the consumption function, followed by a sequence below, followed by another sequence above, and so on. If UT is high and positive, it means that consumption is abnormally high in period T. So you see there, consumption is abnormally high. And why is consumption abnormally high? It's probably because we're in the middle of a consumption boom. Now, if we're in the middle of a consumption boom, we expect consumption to be high again in the following period. Likewise, if the error term is negative, that means probably we're in the middle of a slump, and slumps last for several time periods. So if we have a negative error, we expect the error to be negative again. So this is the reason why we have a relationship between the error terms in consecutive observations. And this is called the problem of serial correlation. In this situation, we say there is a problem of positive serial correlation. It's positive because there is a positive correlation between the error terms in two consecutive periods. So positives followed by positive, negatives followed by negative. And that's what we mean by the problem of serial correlation. The consequences of serial correlation are the same as those of heteroscedasticity, namely OLS estimation becomes imprecise because we're not taking account of all the information when we use OLS. Also, the estimated standard errors are incorrect, so the T ratios and confidence intervals are incorrect. And then there's one more assumption, which is assumption 6. The explanatory variables are non-stochastic. And I better stop there because it's almost 3 o'clock. So I'll start the next lecture by going through this last assumption, and then I'll start on testing in the multiple regression model. Now, in the simple regression model, the only test we looked at was the t-test. And you use a t-test when you want to test the significance of a single variable. But when you're in a multiple regression context, you often want to test a group of variables. You want to test what's called a joint hypothesis, and for that we need the f-test. So this is what I'll be introducing in the next lecture, which is next Monday. As I said earlier, the workshop 4 involves some data sets, the dataset Milk and the dataset Phillips. I'm going to put them on the Blackboard site shortly, so you can start working on these if you want to before the workshop. Any questions?